In this video, we're going to be talking about permutations and combinations. We're going to talk about what each of those things are, how they're different, and also how you would calculate each of those. So we're going to start with an example here. Our problem says that a president, vice president, and treasurer need to be selected from the following representatives: Thomas Jefferson, George Washington, Benjamin Franklin, James Madison, John Adams, Alexander Hamilton, Thomas Paine, John Jay, and Patrick Henry. How many different ways can the three positions be filled? And so what's important here is that we have 3 spots to fill. And I need to think about, okay, what are the different ways I can fill each spot? So for my first spot, that's a little unnecessarily fat, that line. That's okay. My first spot is for president. That's better. Then my next spot is for VP. And my last spot that I need to fill is for treasurer. I'm just going to use a capital T for that. All of these spots need to be filled from this list of 9, if we count them: Jefferson, Washington, Franklin, Madison, Adams, Hamilton, Paine, Jay, and Henry. There are 9 total guys there. I need to choose from those 9 guys one person to be president, one person to be vice, and one president to be treasurer. So if I think about this, I have 9 people to choose from. Any of the 9 could be president. So I have 9 choices for president. Okay. Now, once I've put somebody at president, it could be any of the 9. I have 9 choices. Okay. Maybe you like Washington, maybe you like Franklin, maybe you like John Jay. Any of the 9 could be president. Once I put that person at president, they can't hold any other position. So that leaves me with just 8 choices for VP. Again, anyone can be vice president except for the one guy that I chose to be president. So once I choose somebody to be president, I now only have 8 choices remaining to be vice president. So now I've put 2 people in the spots, 1 for president, 1 for vice president. That leaves me with 7 possibilities for treasurer. I can pick any of these 7 guys except for the 2 that I've already chosen to be president and vice president. So I have 7 choices now for treasurer. Now, again, I have 9 different choices for president. I could choose Thomas Paine to be president if I wanted to. Then for that choice of Thomas Paine, I have 8 different choices for vice president. And if I choose Paine to be president and then Hamilton to be vice president, for that combination, or for that grouping, for that ordering, I should say, I shouldn't say combination, that's a special word here. So for that ordering of Paine as president, Hamilton as vice president, I have 7 possibilities for treasurer. So in total, I have 9 times 8 times 7 possible ways that I can put this ordering of people: 1 vice president, 1 president, and 1 treasurer all together. If we multiply that all out, we get 504 different ways to do this. Okay, 504 different ways to do this. Now this problem is an example, a permutation. Permutation is just an arrangement or a listing in which order is important. The order that I write the 3 guys down does matter. Putting Washington for president, Jefferson for vice, and Franklin for treasurer is different than putting Jefferson for president, Washington for vice, and Franklin still for treasurer. The order that I choose these 3 guys matters, so we call it a permutation. Now there's this formula here that we can use. It's a nice formula, it's helpful, but really you don't need it for permutation. The main reason we like the formula for permutation is it makes the formula for combination a little bit clearer as to why it works the way that it does. But let's just do a quick explanation of what this formula is saying here. We have a little n, a big P, and a little r. N is the number of things I'm going to choose. Oops, watch that. Let me be careful how I say that as well. N equals the total number, stop that. N is equal to the total, oops. Sorry, I had some technical difficulties there real quick. N is the total number of objects. I like to use the number sign. N is the total number of objects. Now you might say, there's no objects here, there's people. Sorry, for me, people are objects. That's how we do in math. R is the number of objects chosen. And again, yes, people are objects. Number of objects chosen or selected. So in this example, we had n being 9 total guys that we could choose from. We were choosing 3 of them, so R is 3. When I plug this into the formula, we have on the left side doesn't really matter, nothing happens on the left side. It's just a way to write down what we're doing. We're taking 9 things, and we want to know how many different permutations I can make by choosing 3 of those 9. So this is 9, the exclamation point. Yes, it does mean I'm excited, but it also means factorial, which if you don't know what that means, we'll discuss it in just one second. So 9 factorial over, in parentheses, 9 minus 3 factorial. Now the factorial, the exclamation point, means 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Yeah, fit it all in. On the bottom, when I simplify inside the parentheses first, 9 minus 3 is 6. So 6 factorial will just be 6 times 5 times 4 times 3 times 2 times 1. Factorial just means start at some integer, multiply that number, that integer, times every integer less than it, all the way until you get to 1. 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now what's nice here is that things will cancel out for me. Because I'm multiplying on top, multiplying on the bottom, and I'm dividing the numerator and the denominator, 6 divided by 6 goes away, 5 divided by 5 goes away, 4 divided by 4 goes away, 3 divided by 3 goes away, 2 divided by 2 goes away, and 1 divided by 1 also goes away, even though I don't really care because I could leave it in and it won't change anything. So I am now just left with 9 times 8 times 7, which we did on the last page and got 504. And again, you might be thinking, well, what was the point of that formula? We'll get to why we need that formula in a second. The formula is mostly useful for showing us why the formula for combination works. It's sort of a stepping point for our combination formula. All right, let's look at a similar but slightly... So in this example, a 3-person independence committee needs to be selected from the following representatives. Same 9 guys: Jefferson, Washington, Franklin, Madison, Adams, Hamilton, Paine, Jay, and Henry. How many different ways can the committee be formed? Well, you might initially look at this and think, well, I still have 9 guys. I'm still choosing 3 of them. So it should still be 504 possible committees. But what we have to remember is that in the first problem, choosing, well, if we look at our possibilities again here, we had president, we had vice president, and we had treasurer. So then when I choose Washington for president, Jefferson for vice, and Hamilton for treasurer, that was different than choosing Washington for president, Hamilton for vice, and Jefferson for treasurer. So those two things used to be different, but now if I'm just making a three-person independence committee, those are the same. It's this, no matter what order I put them in, the committee is the same. So let's look real quick at how many different ways I could rearrange these same three guys. I could also, instead have made Jefferson president, Washington vice, Hamilton treasurer, Jefferson president, Hamilton vice, Washington treasurer, or Hamilton president, Washington vice, Jefferson treasurer, Hamilton president, Jefferson vice, and Washington treasurer. So these three guys, same three guys, used to be able to be arranged 6 different ways. Now, all 6 of these are the same committee. Same committee every single time. Don't waste your time putting them in different order. It don't matter. They are the same committee. So what we need to recognize is that no matter what 3 guys I choose here, I'm just going to shrink this down just a little bit here. No matter what 3 guys I choose, I can rearrange it all day and it does not matter. What we have here is what we call a combination. Order does not matter. So let's look at the definition and the formula for a definition. Like I just said, is just like a permutation. It's an arrangement or a listing, but this time order does not matter. My formula for my combination looks very similar to what we had before. Again, n here equals total objects. R here is still number of objects I'm choosing or selecting. Same as before. And the formula itself almost looks the same as before. Since this is the same, I'm just going to move it off to the side. The formula almost looks the same, except that we see this extra r factorial on the bottom. Now, why would I have an extra r factorial on the bottom? That's to divide out all the rearrangements of the same 3 guys. Like we just saw, selecting the same 3 guys used to give me 6 different possible orderings of president, vice president, and treasurer. Now, those 6 things just become one committee. So I need to divide out that 6 for each group of 3 guys. So if, for this example, we again have 9 guys, but this time we're making a combination with 3 of them, and I want to know how many combinations I can make by choosing 3 things from 9. This time, we still have 9 factorial on top. We still have, in parentheses, 9 minus 3 factorial on the bottom. But now we have this extra 3 factorial. Just like in the last one, when I write out the 9 factorial, and then and then in parentheses I'll get 6 factorial. Everything is going to cancel out except for the 9 times the 8 times the 7. But this time I still have a 3 factorial left over, which is 3 times 2 times 1. 3 times 2 times 1 is 6. So I have on top the same thing I used to have, 504, but I divide it by 6. Why by 6? Well, first of all, because the formula says divide by r factorial, and 3 factorial is 6, but also because any grouping of 3 guys could be rearranged 6 different ways. But with a combination, I don't care how many different ways I can rearrange it. It's the same 3 guys. It's just one committee. So I divide that by 6 and I get 84. So what you have to understand is a permutation order does matter, a combination order does not matter. So when you have a question asking you how many different groups you can make or how many different ways can you arrange these things, the first question you ask yourself is order important? If order is important, it's a permutation. If order is not important, it's a combination. And you have a formula for each. And hopefully you understand why each formula works the way that it does. So that is permutations and combinations.